Welcome to this management science tutorial entitled Shortest Path. Here we want to transport oranges from Los Angeles to St. Louis via the shortest path. So how are we going to go about that? Well, we want to use Excel to solve that problem. So that means we are going to add all edges into Excel. Then define some decision variables, formulate the source constraints, the balance constraints, and the destination constraints, and then finally say the objective is to minimize our distance. So since I'm going to transfer this graph into Excel, I'll probably just put it immediately into Excel. So I'll select that and copy the image, go to Excel, paste it there, and hooray, I've got it. A bit too big, but never mind, I'll just resize it. And here we go. Now the network into Excel. That means we'll take the from node to node and time. So that means from node 1, that's Los Angeles, to Salt Lake City, that's node 2. It takes 16 hours. That's a long drive. Good, let me just resize the columns a bit. Good, so next, what other possibilities are there to get out of Los Angeles, where the orange company is located? Well, I can go to Phoenix, node 3, or Denver, node 4. To Phoenix, according to this graph, it takes 9 hours. To Denver, 35 hours. What a long drive. Good, next one, systematically I use the node 2. 2 can go to 4 and 5. Times are 12 and 25 hours respectively. Then I take node 3. Node 3 can go to node 4 and node 6, Denver and Dallas. Denver and Dallas, which it takes 15 hours to Denver and 22 hours to Dallas. Node 4, our hub, can go to 5, 6 and 7. 5, 6 and 7 with what times? 14, 17 and 19 hours. Almost done. Node 5 goes to node 7, which takes 8 hours, and node 6 goes to node 7 with 14 hours. Perfect. So as you see, I have entered here a directed network. If I would love to have an undirected network, then that's actually pretty simple and easy to achieve. I just have to copy these nodes over here, these nodes there, and duplicate the times, assuming it takes the same time each direction, and I would have the undirected graph. That's good, however, since I have actually mentioned here that I'm using a directed graph, I shouldn't really use them. Okay, well, since I've done the whole work, I'm just going to copy the sheet for later references and delete out of my sheet 1 and these additional ones. Okay, our next task is to actually think about the decision variables. What is the decision variables which I'm going to use? I'm abbreviating it with DV, decision variable, and basically I can make the decision to use the link from Los Angeles to Salt Lake City, or not to use it. These are 0 or 1 decisions. Use it or not use it. Okay, I'll initially say I don't use any decision variable. Furthermore, I'm going to make it look a little bit more fancy and put a nice icon there. So now I should at least have one. Do you see that it works? Great. Now, constraints. Constraints. Well, basically for each node I'm going to have a constraint. So 1, 2, how many nodes do I have? 7 nodes. Let's have a look at our source constraint. The source is Los Angeles, and the constraint is, well, we have to at least use one of these roads out of Los Angeles. We have to leave it. Formally, I would write it as an equation. Going to use that. So decision variable x, and I have to leave arc1, 2. Could use arc1, 2 or some others. Let me just copy that. So x1, 2, x1, 3, or x1, 4 are my options. These are my 3 options. And one of them, at least one of them, must be 1. So, just an alternative formulation. How do I put that into Excel? Well, I just say the sum of these 3 arcs, of these 3 decision variables, must be 1. So, if this is 1, then I'm happy. Alright, where are we in our task list? Provide arbitrary decision variable, formulate a constraint for Los Angeles. Now let's consider node 2. Node 2, Salt Lake City. If we decided to use the arc 1, 2 to Salt Lake City, then we definitely have to leave Salt Lake City again. Either using the road to Des Moines or the road to Denver. So formally, that would mean if we used x1, 2, then we have then the sum of the 2 decision variables 2, 4 and 2, 5. Oops. 2, 5 must equal x1, 2. So now we see it gets a bit tough, and I need to figure out a nice easy way to actually sum up whatever goes into 2. So this sum of what goes into 2, which is only 1 term actually, and have to leave again, which means what variables are that actually. So x2, 4 and x2, 5. So 2 and 5. So these 2 must be equal. So this decision variable must equal this and this decision variable. So as you see, that's not the case right now. I could easily amend that and say, ah, yeah, now it fits. Yes. Now let's imagine we have got lots and lots of decision variable here, and we don't want to do that manually. We want to think about what we have just done. So we said the sum of all incoming args equals the sum of all outgoing args. Okay, so the sum of all incoming args, so this were 1, 2. So sum if is the function which we want in Excel. So you, by the way, you can always find functions here. You just say what you want to look for. So here we're looking actually for a conditional sum, and hopefully you'll find something. Yes, you find something indeed. And then you could just select that. Okay, or you know it and you write it directly. Sum if range, the range which we would like to check. So we would like to check the incoming args, which is the ones which go to, and the criteria which we want to check here is it should equal to this node. Okay, I'm just going to connect this with that, and we should have a string which compares it now, and then I'm just going to sum up the decision variables, which is currently 0. So if I would have this one as a 1, then it works. So that's great. So that's where the incoming args, incoming args. So the outgoing args, that's basically the same game. So I could just copy that formula basically, maybe fixing a couple of cells. Range, the decision variable range will not change. This one will change, but I don't want to move it that far. So I'm just going to fix the B column as well. As a general rule, you actually should only fix what you really need to fix. So here I fixed a little bit too much. Should only say the column is fixed. And here F5, actually also just want to fix the column F. So you can change easily between this fixation of the cells with the F4 key. Okay. Perfect. So now I can drag and drop. That was the whole point of fixing cells, and should have the same formula more or less, which I don't actually want because I want now the outgoing args. So I'll just move that over there, and as I see, nothing is going out from 3, 4. That's why the sum is 0 right now. So if I enter something outgoing, then it's 1. If I enter another one, it's 2. So it seems to work. Perfect. So since we have fixed so many cells, we could just propagate that to the other nodes, 3, 4, 5, 6, which we should double check whether our fixation really worked, and that did not work that well. I should have fixed the range as well. Okay, so let's go back to where we started the fixing. So I should have fixed the rows as well. Okay. Of course I made that mistake on purpose so that you can practice the fixation of the cells. And here we have to move that again. And now we check how does it look. Colors seem to be alright. We have got 6 here and some if. So we have got someone incoming into 6 actually already. Who goes into 6? This one goes into 6. So if I set this one to 0, nothing should come in. If I want to have something outgoing of 6, it's the only one who can go out of 6, I'll do it. Okay, so we have tested the Excel formulas. So we've got one more little tiny thing actually which we want to have is St. Louis is a special case. St. Louis is our destination, and the destination means that the sum of all incoming arcs must equal 1. And so we can just use the incoming arcs. So someone is already incoming into 7. This is this one. And so I could have now 2, 3 incoming arcs even. But actually only 1 lorry should come in, because we are only sending off 1 lorry. So we have got some constraint violations right now here. So now that we have got that nicely formulated, it's time to actually put this problem into the solver and see whether we can actually find the shortest path, which we almost see with our naked eye. So let's see whether we've got solver somewhere. Usually that's in data. I don't see the solver here, so we will probably have to activate that. Options, add-ins. So these are the typical Excel options, add-ins, and we are going to have a look at the Excel add-ins, and we are going to use the solver add-in. Okay, now here, so the solver has appeared in my data ribbon. Let's see how the solver looks like. Okay, it looks nice and neat. It says set objective. Well, the objective is to minimize the total time. Where's our total time? We don't have any total time yet. Ah, nice try, but back to the start. So if we use a link, then we have time. Used time. So that basically means we just multiply the decision variable with the time, then it's used. So we have used here several decision variables and several times. So what is the total time which we used? Let's just sum that up. Sum of all that stuff, and we see 93 hours. Okay, so that's our objective, to minimize that. Subject to constraints which are based here. So we have got here constraints, as we see. So these are our constraints. So x12, everything which comes into Salt Lake City must go out. The source, someone must must go out of this one. So here we see a little inconsistency actually. So the outgoing arcs must be 1. So just to be consistent, actually should probably get rid of my first attempts and copy that up there. Now we've got this nice beautiful formulas there as well. Let's think again. Los Angeles has to have an outgoing, and that one must be exactly 1. They are a bit special, it's not really incoming, but kind of. Okay, so now we are fully equipped with consistent variables. So we have always an equal sign. So the sum of all outgoings must equal 1. That's exactly what we had here. Yeah. So we have equality all the time. Okay, solver. Set objective. That's this one, 93. We want to minimize that. We don't want to travel too long by changing which cells? Well, the decision variables. These ones. Subject to which constraints? Well, or those. Incoming must equal the outgoing. And here we are. Which algorithm? Well, let's try the Simplex algorithm, one of the most classic linear programming algorithm. Also, we've got actually an integer problem here, but close enough to a linear problem. And solve. Solver found a solution which has the value of 43. Okay, we keep that. So our solution is 43. These decision variables were changed. Let's see what happens. So he suggests to go from 1 to 3. Okay, 1, 3. Then further 3 to 4. Then further 4 to 7. Which confirms exactly the route which we would have chosen as well. Obviously this should work also for the undirected problem. And I hope you enjoyed it, and I'm looking forward to seeing you to the next tutorial.